Hello and welcome to this lecture on k-nearest neighbors techniques. In this lecture we will introduce a new supervised learning approach called k-nearest neighbors, and a broader thing that we're trying to do with this lecture is by introducing this technique and comparing it to something that you're already familiar with, which is regression analysis. By doing that comparison, we are hoping to kind of illustrate and help you appreciate two very different styles of performing a supervised learning analysis, and therefore the process of prediction itself. Two very different approaches to prediction, and it's kind of important to know that because up until now you've heard of what supervised learning is in theory, and the first technique that we've gone into and explained is regression, which is a certain way of, for instance, performing a prediction. The hope is by introducing k-nearest neighbors, you see a very different way of achieving the same goal, and it's important because you'll realize that a lot of other machine learning techniques take inspiration from this approach. So this dichotomy, if you will, was something that was first pointed out by Leo Breiman, a very famous statistician, where he said there are two very prominent cultures to statistical modeling. And out here he was primarily talking about supervised learning approaches, and he highlights, and there's some amount of overlap and so on, and I wouldn't really say these two cultures are two different. It's not like a classification as much as two very different styles. And the idea is that he says, look, there is the data modeling approach, which is what you, for instance, saw in the standard regression, where you have some output variable y, and you kind of envision this output variable as some function of your input variable or variables x. So for instance, you would say y is equal to some f of x, and plus there is of course some noise. In the case of linear regression, and here I've kind of shown you an example of multiple regression, this f of x becomes fairly straightforward. It's some intercept plus beta 1 x1, beta 2 x2 for how many ever input variables you have. Suppose you just have one input variable, that would be beta 0 plus beta 1 x1. It's fairly straightforward. So the point he makes, and it's a generalization because he says this about many other statistical methods, which he says you have this whole breed of approaches to supervised learning which capture a functional relationship between y and x, and that function is in some sense cast in stone, and the only job you're left with is to go get the data and figure out what the parameters are of the function, these betas. Your job is to take some data and figure out the betas. This functional form itself, which is that in this case of the linear regression, that it's a linear combination of the different inputs plus some Gaussian noise, that's for instance cast in stone. And he says that you have those approaches, and then you have an alternate breed of approaches, and he calls them the algorithmic modeling culture. So the first one he calls is the data modeling culture, which is and the best example of the data modeling culture is the multiple regression. So we've covered that in good detail in this in the previous lectures, right? So he says, now look, there is another approach. Another approach is what he calls the algorithmic modeling, and there he says essentially the focus is not as much on a rigid mathematical model that you have presupposed, that you have a priori, and that creates this relationship between y and x, which is already cast in stone. But instead, you really have a set of algorithmic instructions or algorithmic ideas that relate the independent and dependent variables. So y is, in the loose sense of the word, a function of x, but that is really captured by algorithms rather than rigid mathematical models. Now, these two, there's a reason why in the start I said these are not like two classifications, but there are more two styles, only because you can describe any algorithm in a mathematical form, and perhaps you can describe the math in an algorithmic form. But what I'm going to do is I'm going to explain to you the k-nearest neighbors approach, and we're going to talk about the k-nearest neighbors approach as an example of the algorithmic modeling, and hopefully at that point it becomes really clear as to what the stylistic difference is between these two approaches. Okay, so let's look at how a prediction task happens with your linear regression approach. The way it happens is you have some data, right? And right now I'm focusing on the graph on the left hand side of the screen. You have some data. You do a regression analysis, and what does a regression analysis do? It fits a line through the data. It fits a line, and if you're using ordinary least squares regression, it fits a line that minimizes the squared deviation between the data points to the line, and so it chooses a line that achieves this target. Okay, so you fit this line. Now what do you do when you need to make a prediction? Right, someone comes along and says, oh great, so you've done a regression analysis, could you tell me what y I should expect for a given x? So they come and they give you an x, so they give you this x, right? And let's call it x, let's just call it x1. Okay, so they give you an x1 and say, can you tell me what y I should expect? And what you do is you draw this straight line up like it's already there, and you say, oh, let me see where what value of y I would get based on my fitted model. So I basically take this x value, draw a line up to my regression fitted line, and then see what the height of that point is. So this is my predicted y, so maybe y hat of 1. So if somebody comes and gives me this x, all I've used all of this data to create a line, but then after that I can lose these data points. These data points can be erased from my memory. All I need to do to make a prediction at this point is I need to know this line, and this line I've already created with the regression, right? So I've created this line, I have it from my regression, and if someone comes and asks me a question as to what y would you see with a particular x, as you know, this line has a form y is equal to beta naught b naught plus b1 x, right? So if someone comes and gives me a particular x, so call it x1, I'll just substitute this x1 out here. I know the values of b1 and beta naught from the regression. That's how I was able to plot the line. I will then just get a y, because I know all the three terms on the right hand side. So I'll get a predicted y, and that's my prediction of what y I will see for a given x. Okay, so that's how a prediction task takes place with the regression approach. Now let's take a look at how the k-nearest neighbors approach works. The way the k-nearest neighbor approach works is that I don't fit a line. So I don't have a line, or I don't have a mathematical form. The idea behind k-nearest neighbors is that if you come to me with a question as to, hey, can you predict for me what y I will see for a given x, I'll take the given x and I'll ask myself who its nearest neighbors are. So somebody walks up to me and says, can you give me a prediction of y for this x1? Okay, let's not call it x1, let's call it x star maybe. So x star, for this x star, because x1 tends to have this connotation that it is the first data point, so I'm going to call it x star. Okay, so for this x star, can you tell me what my predicted output would be? Now remember, I don't have a fitted line. This is a completely different approach to making predictions. But what I do is I go to this line, and on my x-axis, on my input variable axis, I try to find the nearest neighbors of neighboring data points to the x under question, right? So clearly this data point is kind of close to this line, and this data point is maybe close to this line, and so on, right? And the idea is that this KNN approach has a parameter which is k. So let's say I had chosen 5 as a parameter, and you'll understand what that 5 means. It just means I'm looking for the 5 nearest neighbors, defined by the distance from my point under question. So this distance, I want to see the 5 closest data points. And if I do that, for instance, I see that these 5 data points are the ones that are closest. Okay, so what do I do once I've identified the 5 data points? I take their average y's to make a prediction. So I take the average of this y, so let's call that y a, this y, yb, and so on. So if I do the same thing for this data point, this data point, and I take the average of all those 5 specific y's, and that's my predicted y. Okay, the predicted y is the average, and there are many modifications to this. Sometimes you don't take the average, you might do like a localized regression there. There are other ways where you don't just take the arithmetic mean, you might take the median, you might do other things. But the core approach with k-nearest neighbors is that you have not fit a line, you have not created any mathematical abstraction of the data. You've not abstracted away from the data. For instance, in the regression, remember I told you if I need to do a prediction task, I don't even need to remember the data points. I can throw all my data points away. Once I've used the data points to create this line, I now only need the line to make a prediction. I now have a y is equal to f of x, right? So I have this functional form, and I just need to plug in my values of x that I want to use for the prediction, and I'll automatically get a predicted y. Here we are not doing that abstraction. We are retaining the entire data set of points. In the k-nearest neighbors approach, we need all our data points. Now you come and ask me a question about a particular x. I'm going to go and look at the nearest neighbors of that x. And if it's 5 nearest neighbors, I'll look at the 5 nearest neighbors. If it's 10 nearest neighbors, I'm going to look at the 10 nearest neighbors. In all these cases, I'm going to look at the nearest neighbors and either take a vote if it's a classification problem, or if it's a regression problem, I might choose to take something like an average. Okay, so that's fairly clear, and this line that I show is kind of what is approximately the arithmetic mean, and we use that, and finally that's the output that we're going to predict. Okay, now that should kind of illustrate k-nearest neighbors for you. It's a fairly simple technique. A lot of the focus in using this approach to solve problems is based on because it's computationally very hard, because you're storing all the data and you need to sift through all the data to find the nearest neighbors. A good amount of the focus is on the data mining aspect or the computational aspect of using something like that. But it's also very convenient when you have no idea as to what the functional form is. So suppose the linear regression approach can be very useful if you believe the relationship between y and x is this straight line. But if you don't want to make that assumption at all, a k-nearest neighbors approach is fairly flexible to any functional form that y and x could have. Okay, and there are 2 points to note here, just in addition to what we've discussed, which is this k-nearest neighbors approach obviously works when you have multiple input variables. So the example that we took in the previous case, there was one input variable and then there was this output variable, right? This is the output variable. Now what if you had multiple input variables? The same idea. So here we have one input variable on the x-axis, one input variable on the y-axis. So where is the y? Where is your output variable? One way to think of it is that it's coming out of the screen. Essentially, we are not able to, in a 2-dimensional screen, show you the 3 variables. But if you assume that y is kind of coming out of the screen, you could graphically represent it that way. But the important point that I wanted to make here is that if you needed to take like a 5 nearest neighbors approach on 2 input variables, you can still do that. Let's say you were interested in this particular point marked with the x. Then your nearest neighbors to this x again get defined on the 2 dimensions, right? So it could be this point, perhaps this point, and what you can see is we're taking some form of like maybe Euclidean distance, right? Because the distance itself is not just on the x1 axis, it's not just on the x2 axis, it's on both x1 and x2 axis. So you could still use the concept of the input space, and once you have more than 3 or when you have 4 or more input variables, you're talking about a hyperspace. But just you could still use some simple measures of Euclidean distance or some measure of some other distances. Some famous ones are called the Manhattan distance. Some of them are called the Mahalanobis distance. distance as well. Okay. Now the good thing with this approach is that you can even use it for classification problems. If you briefly remember in the previous lecture, we distinguished between supervised learning tasks, which basically just means you have an output variable and you're trying to predict that output variable from the input variables. But this output variable can be continuous quantitative, which is where we've primarily talked about regression and so on. But it could also be a categorical variable. So I've taken an example out here on the right hand side where you have two input variables, x1 and x2 are two input variables, and your output variable is a categorical variable with two classes. So think of it as male or female, or buyer, non-buyer, in a marketing context, defective product, not defective product in a manufacturing context. So let's say this output variable, which is a categorical variable, is represented by either circles or squares. Okay, so the orange circles are one class of the output, the blue squares are another class of the output, and x1 and x2 are just your two input variables. Again, out here you might be interested in, for instance, making a prediction out here, and you might take the 5 nearest neighbors. Perhaps it'll be this and maybe this. So these might be the 5 nearest neighbors, and because you need to predict, right, whether it will be class A or class B, you might want to take a voting approach. Or if your approach is to predict the probability of it being circles or squares, that's what I'm calling as class A and class B, then you might just take the ratio of circles to squares in your nearest neighbors. But the idea is that this is also works perfectly well. You don't need to just take an average. You can take, ratios, or you can just make them all vote. Essentially, the majority wins. So if you have 3 squares and 2 circles, so I'm going to predict this is going to be a square. You can use a voting approach to say it belongs to a particular class. So I hope that gave you an idea of k-nearest neighbors, but also more importantly motivated to you the idea that you have this regression style approaches where you've got this explicit data model. So this is your regression style approaches, where you have a functional form and then you try and figure out parameters. But you can also take on a very different approach to the process of predictive analytics, which is to the process of prediction, where the importance is not as much on that functional form which is cast in stone, which is really an assumption you're making about the relationship between your input and output variables, but it really goes beyond that, right? Like you don't want to make those assumptions, and you just want to take a more algorithmic approach to this entire process. And you'll encounter a lot of the machine learning techniques that we're going to be discussing later in this course really belonging to that class. So I hope that gave you an idea of both k-nearest neighbors and this dichotomy that we kind of see in machine learning. Thank you.